Hello.
Hello.
Hello. Afternoon.
Yeah.
I gave the reading a go. It made my brain hurt.
Which one?
Lambda calculus.
The tutorial. Week 3 tutorial.
Um, the week 2 one. It was the Lambda calculus book, chapter 1, I believe.
Yeah.
Yeah, it made my brain hurt.
Good.
Uh,
It's supposed to. Hopefully, it will become clearer
Yeah,
today.
I was hoping
it
today.
is
I was hoping like today when we go through it, like in the lecture, we can go into more depth. So
I think for the lambda calculus, you want to start with left depth. You know, if you think of it in terms of just functions as you used to in languages, and then delve into the academic style that's kind of presented in the reading.
I think by more in depth, I mean sort of like you can't ask the book questions.
Yeah.
That's
That
what I
is a
mean.
difficulty that books have, unfortunately.
You can ask the book questions. If it starts answering you, you should be worried.
That would be like
That's the
on
kind of
on
answer I
on
expect
the
on this
on the
level.
on the one hand, that'd be a very useful book. On the other hand, I can't help but think of the monster book from Harry Potter.
Yeah.
Tom,
It
Tom,
would be a
Tom
very
will
helpful
buy
book. It's called Gilgamesh Bash. That's the name of that book.
Oh, I've got that book actually. I ordered it a few days ago. I've now got it, and it doesn't have all the horrible typos that the scanned copy
Scan
does.
version.
There's a nicer version on Blackboard now that I found
Nice.
of those chapters, but you should still buy the real one anyway.
Yeah.
I have the one
I'm
book
It's an
over there.
I'm just
extremely beautiful thing to have.
I'm just confused as to how the hell they got those errors into the like. If they were just straight scanning it, it shouldn't have. There was a.
Text, what's
Okay,
it called? Character
it's
identification band.
2 o'clock, so we can officially start. Well, welcome back, everyone. Yeah, I guess we were already chatting about how a couple of people were getting on. How has everyone else been getting on? What have you been reading and working on from this module recently?
I finished my MU. Well, I did a thing in Godot. I did like a visual thing for like manually calculating MU bits and also displaying a full tree of MU,
Ooh,
MI
okay.
theorems. If you want to, I can show it
You,
on. I can
yeah,
share
yeah,
it.
yeah. Let's
Uh,
show and tell, please. Please do.
um, just need presenter
I
access.
need to make you a
Okay,
presenter.
share.
Yeah. Yeah.
Yes.
Is anyone not getting on okay? We always hear from the people who are doing amazing things. Is anyone just totally lost and confused yet? If you're totally lost and
Yes.
confused and don't want to admit to it, then do send me an email or something to let me know. So, Matthew, do you have your thing ready?
I think you made the wrong Matthew presenter. I think you made
Yeah.
Mr. Murr a presenter rather than me.
Yeah, that should be it. Try. Oh, hang on.
Oh, there it
Yeah,
is.
try
There
now.
you
Try now. There you go.
go. Right, share application screen. Screen one. That should work. Can you see the screen with the Godot on it?
Okay. Yep.
There you go.
Looking
Where's it
good.
gone? Right. Here you are. Well, there's this one which is essentially just generates the theorems manually, so it'll give you the options of what you want from there. So I can double it here again, and it'll give me all the possible outcomes from here. Double it again, it'll give me again, and it gets quite complex after a while. It generates a lot quite quickly, and then Godot really starts to lag when I do it again because it's generating so many draw calls for buttons, it doesn't like it. So yeah, there's a few too many options for it. But
Is it
essentially,
interactive then? Are you clicking on the path that you want to take? Yeah.
yes. So this presents every single possible combination of what's it called, bangs as possible.
Bangs and pops.
And yeah, bangs and pops as possible. And as you can see, there's quite a few. So if I wanted to like turn half of the string into use, I could do that. It would give me it back. It will take a few seconds.
Very nice. So
Lagging,
why is it maxing out at a certain size, do you think?
Well, it's not the problem with well, I mean, the computation expense is not actually on the actual calculation itself, but it would be eventually if you get to a certain level, because especially if you just double the eyes, because then there's because if you have 8 eyes, then there's I don't know how many combinations there would be of bangs you can perform in there inside the set of eyes, but you can change like one each individual one, and then that becomes a set, and then yeah, I mean it's better shown through the tree, but now my program has decided to stop working, so let's just restart it.
Did it suffer from a Stack Overflow error?
It was before, but it does seem to be doing that. Where are you? There you are. Okay, mouse, please stop. Oh. It's a little buggy, as you can tell. There you go. So this generates this breadth first, essentially. So it'll generate a number of levels from this. So it'll generate 3 levels from here, from MI. So 1, 2, 3 here. Once you get to 4, it starts to get a bit complicated. If you give it a sec, it can generate a lot of combinations from the doubles here. And there you go. I spent far too long trying to develop tree structure this for Godot, because Godot doesn't have a base tree structure, oddly, in terms of just like a very nice thing. But that is what I've been doing.
So you've developed a tree visualizer for Godot Engine while you were doing the view puzzle.
Yes, that's a very useful tool that I can put. So
that
yeah, it's not perfect.
A whole bunch of things. Yeah.
Yeah, it could. It's not perfect. It does kind of skew when you zoom in and out. It's not doing it at the moment, which is good. But yeah, it could do with some work. But yeah.
No,
So
I love
that's what I've
that.
been doing.
That's great.
That's awesome, yeah. That's awesome, dude.
Thank
Yeah,
you.
very cool.
Yeah.
Very cool. Well done.
Excellent.
I wonder if it'll be able to do 10 levels.
Go for it.
We might be here for a while.
So
Okay.
people who are in, well, I think everyone's in machine learning last semester. You remember about that one workshop where I think we were playing around with the k-means clustering or something, and we were playing around with how different epochs and stuff, and some of us ended up just basically having a competition of like how far can we push our computers before they melt. What bets do we have on this one?
Well, it's not reached the max level yet, apparently. It's still going. Well, even though it has hit 10, but I'm not sure what it's doing.
And does it ever
So,
find
yeah,
a new?
no, it probably won't. It probably won't.
I think we hope it doesn't. Now. Yeah.
Yeah. Otherwise, it might be a bit broke. But yes, that is what I've been working on in terms of this. It was interesting, actually, to develop the tree structure. So that was the nice thing. But yes.
That's amazing. Does anyone else have anything else they'd like to show or discuss from these workshops and homeworks? Any more versions of the MU puzzle? No.
No,
Or
no
do you
versions
just?
of that. No.
Otherwise, would you like to just tell us what else you've been working on this week? Has anyone been trying to do the readings that I put up on blackboards recently?
Yeah, yeah.
Yep.
Yeah. Did the modal and paraconsistent logic tables, and that worked out pretty well. So it's tricky to start with, but comfortable. Got there in the end, I think, with just trying to think it through. And I
Okay.
put on the chat that if you put TMS 1979 in the search engine, it will give you a podcast that you can happily listen to for 2 hours and realise it's completely the wrong thing that you were referencing on the slide, so, which is exactly what I did. So, I thought it was some meta sort of deep puzzle that was being presented, so I sat there.
It stands for Proof Maintenance System, right?
Yes, it does. Yeah, I found that out now. Yeah, but the podcast was something like this something. But yeah, so that was that. But yeah, the logic tables were pretty good. I think around 2 errors. I think there was 2 typos. So yeah, that was what I'd come through. But it was I think it was on the and table on the bottom 2 left, the T and the B.
Yeah, right. With these two, I think, wasn't it? There was something wrong around here.
Yeah.
And are these
Yeah,
correct
yeah.
now? Is this the version that I fixed? Can you tell?
No, that should be an N and an F.
That should be NF. Okay, so can you explain why?
Yeah, so that if I share, if I can share, I drew it out as an AND
Yeah.
gate. So I'm sure if I share that, I'll just share it and just
Okay.
see how
Yeah.
people saw it, because it took me a while to think. So are you seeing my screen?
Yeah.
Okay, right. So this was the ones I was looking at here. These two. So what I decided to do was just start off and do the table again, and I found that this was called a oh, I can't find it now, a 4-valued logic table. So I was going through trying to figure that, I thought about it with these AND gates we've got here, and if only true is found, then only assigned. So we've got if some are true and the others are false, then both is assigned. If no info is given, then neither is assigned. And if only false is found, then false is assigned. So I found that initially quite confusing. So I was trying to think, okay, when does neither pop in and when does both pop in? So I got the both, but the neither was sort of in trouble there. So these bottoms 2 here, this N and this F, I've true and the false, I've just put 0 and 1, B and N I've kept the same. So this, if we start here, so we've got neither and true. So what I've done is drawn out the AND gate and put neither and 1 for true. And if it's AND, so it should be 1 and 1, I would give a true result. 1 and 0 would give a false. And if it's neither, I just imagine that as, say, a fictional number or a number like 2. So it would be 1 and something that doesn't make any sense. But 1 and something that doesn't make any sense wouldn't provide a 1 or a 0. It would just provide, or a both. It would just provide a neither. So that's how I sort it through the N. And then this one here, the N and the B. So the B is both. So we've got the 1 and the 0. N is neither. So say a 2 and a 1 gives nothing, in that sense, and an N and a 0 give nothing. So that's sort of that's how I thought about. Sorry, N and a 1 give an N and a 0 give a 0, but it needs both. But because but a 0 and an N is equal to 0, so a 0 goes through. I think I've got it somewhere further down here. I'll try and go through it. Sorry. Here it is. This is how I sort of drew it out a bit broader in that sense. Okay, okay, here, yeah. So I sort of expanded this single AND gate into two. So we've got the N and the 1, and then the N and the 0. And the N and the 1 is a 1, an N and a 0 is an N, a 1 and an N, similar to this. I thought was an N, but I've got 0. So anyway, I've confused myself again. So this is where I stuck, but that's how I'd sort of done it. So here we have true and neither assigned because there isn't. Oh, sorry, that's an OR gate. I'm on an AND gate. Sorry, that's why I was confused. So, so anyway, that's the sort of stuff that I'd gone through, and I found that these two sort of errors here, and then I did the same.
If you're working out this interpretation of physical logic gates, yeah, you can imagine neither as representing just the absence of any electrical signal on one of the wires. So in real digital electronics, you'll normally represent 1 and 0 by a high voltage and a low voltage. Yeah. But the neither is like if you actually cut the wire, you just completely remove the wire from the system. So there isn't even a low voltage there anymore. And you'll find that will propagate in that way. So yeah, the AND gate in particular, you can almost imagine it as a switch. You've got one true input, and if one input is true, then it's gating the other input. So whatever is flowing on the second input will flow through because the first input has switched it on. So you should see that that neither propagating or both both can propagate in the same way. Yeah.
Okay.
Okay. Good.
Yeah. So that's what I'd gone. I'll stop sharing.
And the main use of the both in digital logic, it's used a lot, right, in real architecture design. The main use there is to represent what is called don't care. It means you just don't care what the value is. So it's a symbol. I think we've talked a few times about garbage, computational garbage. Sometimes you have a bit that's been produced as a side effect of something, and it just doesn't matter what it is because it isn't going to be used for anything. So you can make your calculations much simpler if you just represent that as don't care and you propagate the don't cares through the system. It will give you the logically correct answers that you don't care about a whole bunch of other stuff coming out the other end. Or if it turns out that you do care about one of those things, then it tells you that you've lost track of it and that you need to go back and sort it out. Okay, good. Anything else from anyone else? How did you get on? Any questions, observations? Anything from last time?
I sort of found something with the para-consistent logic stuff. It was definitely not as impressive as what Gary just showed, but it's sort of there's a line of symmetry down diagonally, and I sort of noticed that the T and the B weren't the same as the one on the other side. So that's sort of how I looked at it, and I was like, doesn't make sense because both of them have the line of symmetries, and they're both like copied over. So I was like, it's not. I couldn't prove it, but I was like, I sort of know there's something wrong with those two at the bottom or the top right. So
back on, was it these two? I think. So you're looking for something symmetric down here with something up here.
With the those. So it would be like the top row, last two.
Because
so it's like there's a line between the middle. It's like if you're doing multiplication, like table thing, there would be a line of symmetry between or like a correlation matrix. That'd be the same.
That's because logical AND is commutative. Yeah, it doesn't matter if you do A and B or B and A. So you should expect that nice symmetry coming down.
That's the one, yeah. That's what I noticed that, but I was like, because it doesn't sound like that's a very provable thing. So I was just like, but yeah.
Yeah. Is it obvious in advance that AND is still commutative when you have both and don't care in play? Maybe it is. Maybe you'd have to think about it.
That's what I thought at first, because I was like, is neither true nor false or both true and false? Could they be messing up sort of the symmetrical like property of it.
Yeah.
But then I was like, I don't think so, because it's yeah, as you said, you could swap around which way you do it, and it would still get the same result. So
Yeah. Okay, good. Nice observation.
I have a
So,
really boring question about the attendance code because I was a minute late. I wasn't sure if it's already been shared.
yeah. Okay. Good point. No, that's an essential piece
Sorry.
of maintenance. Yeah. Give me one moment, and I will pull that out. So today is the 3rd of March. Yeah. So we have two codes for today. This is for the lecture. This is for the workshop. We'll put both of them in text chat. Everyone see those?
Yeah, thank you, Charles.
Yep.
Yeah, good. Okay, so if no one else has anything to report, let's look at some new stuff. So today I wanted to talk about lambda calculus. Actually, before I do the slides, let me just show you the real version. Okay, now you are not expected to understand this. I put this up on week 4 reading. You know, like the Frege paper, it's something for you to look at rather than to really read and understand, unless you're really that good. But I do think it's important that we are aware that papers like this exist and at least have seen them. Okay, so this is Church's original 1936 paper, and this is where a whole bunch of stuff is invented and published. You will see here the creation of the lambda calculus. So here is a lambda. Hopefully maybe some of the introduction of this will make some sense after today's lecture. You know, you can see we're referring to Gödel already on page 2, being very influenced by that. These are what are called church numerals, and we'll talk about them today if we have time. It's a way of defining numbers in terms of lambda calculus. It's defining the numbers 1, 2, and 3. And a couple of other highlights. This is something that is known as the Church-Rosser theorem that we will probably look at next week. A very, very famous theorem of lambda calculus. It's really the theorem of lambda calculus. He's crediting Rosser, who's worked with him on this. It has been proved by the present author and Rosser. Talking about Gödel again, Gödel numbering of lambda calculus terms. It's only 20 pages long, right? And it's doing a lot of very interesting stuff. And here, this is the legendary part. Okay, this is defining the concept of computation, and it's called the notion of effective calculability. We here define the notion of an effectively calculable function. This is going to define what is meant by computation, and this became known as Church's thesis. And you know, all these other models of computation will turn out to be equivalent to it. And if we get right to the end, what you will see here then is a proof of what we now know as the halting problem. So this is saying in terms of lambda calculus, this is saying there's something that lambda calculus cannot do, and therefore there's something that no computer can do. And that problem is to look at one of its own programs and decide whether or not it stops or whether it will loop forever. And so here you see the first proof of that halting problem set up in lambda calculus. But this is one paper, right? It's 20 pages long, much shorter than most papers that are published nowadays, and it does all those things. It sets up the lambda calculus. It shows the Church-Rosser theorem. It defines what computation is, and then it shows that there is an uncomputable problem that the computation sys cannot do. So, please have a look over that paper. Don't try to understand it all, but some of it you will see little pieces of it that link to stuff we're going to talk about today. Some of it will make sense, and maybe over the course of your career, if you want to get deeper into all of this, you'll learn enough to really understand all the details of it. And this paper, of course, is still controversial because people argue about what was due to Alan Turing, who published his paper just a few months later with a proof of some of the same results in it. So let's try to understand what Church did, at least in the start of the paper, when he created what we now call lambda calculus. I'm going to give you an informal version of it, first of all, just to give you an idea of what this is. This is not mathematically correct, but it will give you the concepts. Then I will give you the formal version, which is hopefully correct. And formal versions are important in computation because they're the things that we actually implement, and they have to work if you're going to build real systems out of them. And if we have time, I'll start talking about some of the things you can actually do with the lambda calculus, such as arithmetic. Okay, so what is the lambda calculus? How many of you have seen any of this before? Who knows roughly what a lambda function is? Have you ever used a lambda function in a programming language, for example?
Yeah.
Yeah.
A lot of some programming languages don't. They call it a lambda function, but it's really like an anonymous function.
An anonymous function. Yeah. Yeah. Good.
Yeah.
Good.
So
So
something
you
that
might
isn't bound to. Yeah. Yeah.
So
Like
you
in
might
Python.
have seen things like this. Okay, look, let's start with something that is roughly familiar to everyone. So this is stuff you can type in Python right now. Actually, if you have your Python interpreter available, why not fire up your IPython or whatever right now and try typing this into Python. Yeah. So what we're doing here is creating a function. This function is called f. And as Matthew says, it is an anonymous function. This is the function which takes x as an input and it returns x plus 3. So it's completely equivalent to just saying def f of x return x plus 3. Okay, so has everyone got a Python interpreter handy?
Jupyter Notebook,
Yeah.
here we go!
Yeah. If anyone doesn't have a Python interpreter handy, let us know and we'll try and make sure that you have one. Okay, so what do we get if we enter this and then run f of 2?
5.
Okay, so if you've done that one, then try the next one. Try g. What do you get for g of 2, and what do you get of this g of 2 of 1?
Well, g of 2 will return a function that adds 5 to whatever its next argument is. And then g of 2 of 1 will return 6 because you're applying it to the function that returns 5.
Yeah. Good. So this will give you 5. This will give you 6, and this gives you another function. Yeah. This gives you another function which adds 5 to things. So can everybody run that? Can anybody not run that in Python? Can anybody not run it in Python and wants to admit it?
So when you run the last line, are you calling g and passing 2 and 1? Or are you calling the function g of 2 and passing 1? How does it work in that set of three
Yeah,
commands? Has it
so
assigned the function to g of 2?
so there's really two different ways you can read this. You can either read g as being a function that takes 2 arguments
Yep.
and adds them together and adds 3. Yep. So one way to read this would be equivalent to something like def g y return x plus y plus 3. Yeah. So if you read it that way, it's just a simple function that takes 2 arguments and returns something. That would explain this final line. That reading won't explain this line though, because what you have here is a partial evaluation where you've only evaluated it for the first input x, and you've got back another function. So the other way you read it is that g of 2 gets evaluated and it gives you a new function, and then let's give that a name. Let's call it fun, and then you run fun of 1 to give the final result out. Okay,
Cool.
so I'll go back to the mathematical definitions. So that's just to show that lambdas are not very scary. They're sat there in Python, and you can use them right now to go around defining functions with as an alternative to the def statement. So look, lambda calculus is the first and simplest model of computation. This is all coming from the church paper that I showed you. So the basic idea is what we just saw. Consider a function like this, okay? F of x equals x plus 3. This is how we normally go around defining functions, both in programming languages and in mathematics. So what exactly is this saying, right? You have an object on the left-hand side, you have an object on the right-hand side, and we're saying the two objects are defined to be equal. And really, this should have 2 little dots on the equals, because this is usually being used as a definition. We're saying make f of x become equal to the thing on the right-hand side. So x plus 3 is a mathematical operation. It's a process which happens to x. It's a way of changing x to produce something else, and that's the output of the function. And the left-hand side is defining this thing called f. Its type is a function, so f isn't a variable that just has a simple value like 3. F is a function. It's something which takes an input. In this case, it takes 1 input, and it does something to it, and it returns an output. Okay, so this notation is what we find in most, at least non-functional programming languages. We're creating something called f. We're saying its type is a function, and by that we mean that it is a little computation that has an input, it does something, returns an output. Now, we can write that in an alternative notation, the same function using lambda calculus. And what you notice here on the left-hand side is that f is now sitting all by itself. This is no longer f of x. Okay, so in this notation, we're saying part of f's type is the fact that it takes 1 input and returns an output. Here, we're just saying this is what f is, and that's all. So it's a cleaner definition of what f is going to be. And we read these symbols. The symbol lambda, you can read it as something like the function which takes input. Okay, you can read this little dot as and returns. Okay, so this whole thing then, if we translate this into English, it says f is the function which takes x as an input and returns x plus 3 as an output. So this phrase here, the lambda, means the function which takes x as an input. Okay, this is telling you almost the type of f. We're saying there's something called f, You might want to put a little colon there to show we're defining it sometime. There's something called f, and what this thing is a function which takes x as an input, and it returns x plus 3 as an output. Okay. Now, does that make sense? Does that not make sense to anyone? If you're happy with this English translation of this notation, then you're winning. Okay. Well, this is exactly what you can put into Python. Okay, you can say, as we saw on the slide, we can go to Python and say f is lambda x. It's the function which takes x as an input, and it returns x plus 3. Okay, it's precisely equivalent in the Python implementation. So then if you call that function with a number 2, then you're going to get 5 coming back. Okay. Any questions? Now's a good time to ask questions.
Charles, we've seen, I think, X and Y. Is there a limit to the number of inputs in lambda calculus? Can we have
So
X and Y instead?
You can have as many inputs as you like. So that, I'll just show you the next slide. Yeah, okay, so for example, yeah, let's do this for a function with 2 inputs, okay? So look, traditionally you're going to write something like this, g of x and y. And in this notation, you're saying a lot of things on the left-hand side. You're saying not only that g is something that exists, but you're saying g is a function and it takes 2 inputs and they're called x and y. You're saying all of that on the left-hand side. Okay, if we write the same thing in lambda notation, we'll get this. We will get g is the function. The g on the left-hand side is just a symbol. Okay, the left-hand side only says that there's a thing called g. It's much simpler than all that type information we had up here. The right-hand side now has all the information about what g actually is. So we've written it here as g is a function which takes x as an input. And again, there's 2 ways of reading it. Okay, one way to read this is it's a function which takes x as an input and it takes y as an input. When you've got 2 lambdas next to each other, you can read that as taking 2 inputs in sequence. And then it returns x plus y plus 3. Okay. Now the other way to read this is that g is a function which only takes 1 input called x, and it is going to return this thing. Okay. So in this reading, g only has a single input. So for example, we can evaluate g of 2, okay, or g applied to 2. When we write a number or an input after the function, that means it's going to get plugged in to the argument. So here x is the argument, and we're going to plug in x equals 2. Okay, x is going to take the value of 2 now. So now we take everything here and we write it out again, but wherever we had an x, we're going to write the number 2. So this x has turned into a 2 down here. Everything else has stayed the same as it was up here. Okay. Now if you read it this way, what g of 2 has done is it's taken a single input, it's taken that number 2 as an input, and it has returned a new function. Okay, and what does this function do? Anyone?
It's truly unknowable.
It adds 5, right? This is a function which takes y as its input and it returns y plus 5. Yeah. So this is an add 5 function. So you could equally have written this as something like def add 5x. Yeah. And it's going to return. It's completely equivalent to that definition. Okay, so you know, if you've seen functional programming in other studies, this should look very familiar. It's the idea that a function doesn't just return a number. You can have functions that return other functions as their output, and they can take other functions as their inputs as well. So this is why if you apply g to 2 arguments, as I said, there's 2 ways of reading this. One way to read it is that g is a function with 2 arguments, x and y, and it's going to plug both of them in and end up giving you the number 6. The other way to read it is to do this step-by-step evaluation. You can compute g of 2. That gives you this object here. So this is g of 2, and that's getting applied to another input, number 1. And remember, g of 2 is this function which adds 5 to things. So here you're calling the add 5 function with a single input, the number 1, as its argument. Okay. So yeah, to answer Gary's original question, yeah, you could keep going. You could have functions which take x, y, z, a, b, c, d, e, and so on, taking many inputs here.
In a lot of modern languages, the ideas of first order arguments, being able to treat functions as any other variable. Because of how prominent object-oriented it's become, the idea of a language where everything is an object, like Python, for example, it gets things like this for free, because if functions are just an object, you can treat them the same as you would any other object.
A function as an object, yeah. So you'll see this in some object-oriented languages. Probably not all of them.
No, even things like C#, a lot of functional ideas are coming in because people like expressing things in functional ways. So there's ways, if not of using functions as regular arguments, then casting them or interpreting them in some way that you would be able to use them. I mean, even in C, you have the idea of pointed to a function.
Yeah. So it's pretty common in C to pass functions as arguments. Yeah, we do it all the time in robotics for callback functions. If you want your function to get called every time something happens, every time the robot hits a wall, please call my escape from the wall function. And so it's common in the case like that you pass that function as an argument. Yeah, you say here is my escape from the wall function. Here you are as an argument. Next time I hit the wall, call the function that I just gave you as a callback. So you'll see these things around in probably most languages in some form. In a functional language, it's much more emphasized as a programming idiom, although you can often program like this in other languages as well. So sometimes this style is called currying. You come across this? Currying?
Yeah. If you read enough of the Haskell wiki, we'll shove the word curry down your pile like nothing else.
Yeah. So Haskell Curry was a logician who worked on a load of this stuff, and the language Haskell is also named after him. So he got both his first name and his second name turned into technical terms. So yeah, currying is this idea of a function that you can partially evaluate. So really you want to call g with 2 arguments, but you can stop halfway and say here's only 1 argument, and what I've got coming out is a new function that takes another argument as its input.
It might be worth mentioning that being able to partially evaluate functions isn't just like an interesting syntactic difference, because if you have something that's partially evaluated, then it means that you can compose your programs in very different ways, and you can pass around the partially evaluated form of it instead of having to always require both at the same time, which means that if you have some function that requires something that takes only one argument, you can then give it your full thing that takes two arguments, and then get back the pass you evaluated, rather than always needing to have that form.
Yeah, so look, this style can make your program go faster, right? Because if you've defined this function g, it takes two arguments and it adds them together along with three. You might have a case where you often want to fix x. You really are going to fix x equals 2. So if you're planning on doing a lot of evaluations like g of 2.5, g of 2.7, g of 2.15, it's a waste of time to keep calling this function and doing the addition of x every time. Here you can curry it. You can create an add 5 function by doing this. You do that once. Now you have a function that adds 5 to things, and then you can just put all your numbers into that and do less work to do all those different additions of 5 to many different inputs. Okay. Does anyone not understand? Is everyone happy that this Python code is doing the same thing as the mathematics then? So in particular, this is the interesting line. This is where you see the currying. Here's where you evaluate that g function with only a single argument, and you'll get back this function. You get a new function back. And then here, you're applying that function to the argument number 1. Okay. So if you haven't already done it in Python, please give that a go in Python. And increasingly, you'll find these constructs in other languages nowadays, not just in functional ones. Do we actually have them in C++ now? Do we finally have lambdas in C?
Kind of. They're terrifying though, because they all depend on templating, and
no.
Yeah, but you do have lambdas, and you can use them for really cool things that you wouldn't be able to use other functions for. Because even though you can do things like have path evaluations and function pointers in C++, lambda functions in C++ have particular pieces of syntax that allow you to express. It's like a completely different language implemented in the language again for the 4th time or something. Yeah.
Okay, good. So there's a joke that every new trendy language that comes out evolves to look a little bit more like lambda calculus. Rust and Go and all these things are increasingly taking ideas from here, and yeah, eventually they'll evolve back to the one true way. So okay, look, that was the informal version. Okay, now look, some of the things we've assumed in this version are things like arithmetic. Okay, we assume that we have numbers and we have additions. And what else have we? We've assumed the associativity of addition, right? We've not talked about whether x plus y is, and the commutativity. We've assumed that all these arithmetic symbols behave as they do in everyday mathematics, which is fine for programming everyday Python. But if we want to use lambda calculus as a fundamental model of computation, we're not allowed to assume anything. We have to build this all from the ground up. We're going to have to construct numbers and arithmetic and anything else that we need. So I've given you that informal version just to get a gist of how the lambda calculus works. But now let's look at the formal definition. Okay, this is a formal grammar for lambda calculus. There are slightly different ways of setting this up. Different books will do it in slightly different ways. This is the one that I'm going to use. Is everyone happy with this kind of grammatical definition? Have you seen this kind of notation before?
I've seen it, but I'm familiar with the
Okay.
the diamond
Okay,
arrows.
so this is just about BNF, Bacchus Naur form, and it's a standard way of describing grammars. So, you know, in English, let's make a simple grammar for English. Okay, you could say, I don't know, a noun phrase equals adjective noun. Okay, so the red car. Maybe you need a determinant or something. Okay, red car is a noun phrase. Okay, and then you could say something like, you know, a sentence can be a noun phrase followed by a verb followed by a noun phrase. Okay, so this will define a very simple grammar of English. You can say, you know, the red car hit the orange pedestrian. Yeah. Or you could say the black cat sat on the fluffy rug. So someone's saying they forgot the attendance. It's written on the text chat. I'll just post it in again in case you missed it. There's the attendance codes again. Forgot to do it. Oh well. Okay, so here's a grammar. So should we do a grammar for a simple programming language? Would anyone like to try writing on this slide using the annotation tools and write something a bit like this English grammar, but for your favorite programming language? Anyone want to give us a tiny little grammar for a bit of Python or C or something?
That for a whole language?
Just for a fragment.
So we're not going to write several pages of an entire 1,000-page manuscript for the C++ grammar. We're not going to do that. Okay.
So, you know, for a language like C, you could say something like an expression can be, I don't know, a variable name followed by equals followed by a value. Yeah. And a variable name can be variable name could include any combination of the letters A to Z. So this notation means any letter from A to Z repeated one or more times.
Yeah, and underscores and zeros. But in C, it's not necessarily a variable name. That's generally an identifier because that's the same token that you would use to capture a function name, for example.
Okay, let's just do this for a simple language then, a simple fictitious language, yeah. And then a value could be, say, any number between 0 or any digit between 0 and 9 repeated. That would give you a little fragment of a definition for a language. Okay.
By the way, so your definition for a name means that some of your functions don't work because you said that it's one or more things between A and Z. So x, y, z, x is a single variable instead of being 4.
Okay. Yeah. Okay. For now, then let's get rid of that. Let's say you can just have anything from A to Z. Or if you need more letters, then you're welcome to go and invent them. Okay. Let's say you have an infinite Unicode allocation of possible variable names. Yeah, you're talking about things like this, aren't you? This YZ here, Y and Z are two separate names. YZ isn't a name in this notation. Yeah. Good. Okay. So look, what we're saying then is that lambda calculus is created as a family of well-formed expressions. And here are some examples of expressions that are generated by the grammar. And all of these examples are generated through these rules. Okay, so to make an expression, you can either write down a name, or you can write down a function, or you can write down an application. And then we're going to define what each of these things is. So if you choose to write down a name, that means, yeah, let's get rid of the plus then. If you choose to write down a name, you can just write down a letter between A and Z. Say. Okay, so this is a very simple lambda expression. This is just the letter X, and we've generated it by choosing an expression. We've chosen to do it as a name, and then we've picked a particular letter. So X is a lambda expression. Okay. Or you can choose a function. Okay. So if we choose function here, we're starting by generating an expression. We're going to choose to do a function, and a function has to have this form. So in this notation, it has to be in brackets, and it has to start with a lambda, and it's got to have a name, and then it's got to have another expression. So for example, here is a function. Okay, this has the form of this line, and we've chosen to make an expression. We've chosen to do it as a function, and then we've chosen the name X, and for expression we've just chosen X again. Flashbacks of a really bad C-like interpreter I made during the game jam. Maybe you can make a slightly more beautiful interpreter once you've studied the lambda calculus. That's the.
I hope so. It was a mess. So.
one of the great
fun.
advantages of studying this stuff is that it gives you a mental framework to do things like that very properly, instead of just hacking them together.
I was reading the Dragon book, as recommended to me by Mr. Murr, but it was still a bit of a nightmare to try and get through. It was good fun. I would recommend giving it a go if anyone hasn't done it before. It's stressful.
Yeah, on the upside, lambda calculus is a very simple language, so it's much easier to see what's going on than in any big, real programming language. But think of lambda calculus as a very simple programming language with the minimum amount of rules, or almost the smallest possible number amount of rules to make a programming language. Okay, so I'm going to ignore that one for now. I'll come back to that one later. The other thing we can do is called an application, and this means you take two expressions and you put them together inside a pair of brackets. So for example, here we've got two functions. That is a function, that is a function, and when we put them next to each other and wrap them up in a pair of brackets, that has given us an application. Okay, so when we talked about the mu system, that's a way of generating strings, well-formed formulae. These are the rules for generating well-formed lambda calculus expressions. And can we understand roughly what these things mean now from what we saw informally? What is this? This is a function, yeah? We know it's a function, but what does it do? How do you read this in English?
That function, it takes an input of X and then returns X.
Yeah.
I think it was
So
like
you might, yeah. So often this is called I, it's the identity function, yeah? If you say I equals lambda X, and we're being very formal in this section, so I'm going to do all my brackets very correctly. Yeah, so if I was to define it in this way, I equals the function which takes X and returns X, that's an identity function. It has one input and it returns the same thing as the output. Good. Okay, so how about this thing? What's going on here? How are we going to read this?
That is X.
Mm-hmm.
So that's the application of the function that we just defined applied to X.
Absolutely, yeah. So that's I applied to X, and that is. Be careful with this equals symbol, okay? We haven't really defined equality properly yet, but yeah, roughly that is going to evaluate to x. Good.
Yeah. You're supposed
So
to
this
use 3 lines when it's that kind of equality, because the
yeah, or sometimes you'll see 3 lines and a little beta symbol maybe that I'll get to in a moment. Yeah. Okay. Good. So yeah, that's a mathematical symbol. Yeah, roughly, it means the mathematical values on each side are the same. So for example, you'll see things like this a little bit later on. So look, the function which takes x as input and returns x is, in a different sense, it's equivalent to the function which takes y as input and returns y. Okay, would everyone agree these are the same function? Yeah, it doesn't matter what you call the variable name because they're both just the identity function. But you can see they're not textually equivalent. It would be wrong to say this expression is completely equal to this expression because they're different expressions. Yeah, this has got x's in it and that has y's in it, so there's something different about them. But they're equivalent in the sense of what is called alpha conversion that we'll talk about later, whereas this is equivalent in the sense of something called beta conversion that we'll talk about later. Okay, so how about something like this bottom one then? Can anyone explain what's going on here? Or what's the top level structure of this? Is it a function or is it an application? Does it look like this or does it look like this?
Which one are we looking at?
The last one. The bottom
The
one.
very final one. Oh, well, it's got several different things in it.
Mm-hmm. So what's
say
the top
application.
level? Okay, why is it an application?
Because it seems to have expressions side by side, very like the definition above.
Can you draw on the screen, Fionn? Do you want to
Oh, I don't
underline
know.
stuff? Think about it.
Let's have a look.
Yeah.
So I seem to identify this as an expression.
Yeah.
And that as an expression in the same kind of way that these are presented.
Yeah, good. So the top level structure is an application.
Yep.
Okay. And so what's going on in, let's say, the second term of that then? What's this?
That to be honest with you, I'm not 100% sure.
Would the right side is that just a function? That part,
that's a function.
And then
Yeah.
that's just a function. Then.
So that's the function that takes x as an input and it returns x, y as an output.
Yeah.
And you can read it in English, right? You read lambda as the function that takes x as an input, and then you read the dot as return and returns. Yeah.
Okay.
So it's the function that takes x as an input and returns x, y. You can translate that straight into English.
Yeah, sweet.
Okay, good. So you see the overall structure of this then, it's an application. That's the function that is being called, and that is the input. And as it happens, the input is another function. So we're going to pass this function into that function. And this thing will become x. It will become the argument x when we write all this stuff out. Okay. So again, we're being very formal here. We'll drop some of the formality later on because it can get a bit crazy. But you need the formality if you're actually going to implement this, which I hope you are very soon. We need to define scope. We're really going to define what the lambda calculus does. Okay, so far we've only defined the grammar. Okay, and remember we've got grammar, logic, and rhetoric. Okay, grammar is, in this case, is just the syntax. It's saying all the strings that are valid strings in this system of logic. The grammar is going to be the logical rules so the logic is going to be the logical rules of how we manipulate these expressions. So when we talked about actually applying that function to that argument, we haven't yet defined officially how that is going to be done. Yeah, so far we've only defined the grammar rather than the logic. So I'm gearing up to give you the logic, but before I give you the logic, I've got to define a couple of other things which are called scope. Now, if you have ever had a bad experience with a language like Python on account of its scoping rules, you will already know about this. Okay, if I write a Python program like x equals 1, I'll put that up here, and then I'll write something like define f of y, then I'll define it as return x plus y, okay? And then I'm going to call f of 5. What is that program going to do in Python? You can try it if you like.
Well, if the x is above f or on the same scope as f, then it will return x plus y.
Mm-hmm. And is this a good idea in the design of Python?
It depends on how you want to think about it.
Global's bad.
Yeah, and this is one of the main criticisms of Python, that it allows you to do this, right? In other languages, you will get an error if you try and compile this, because it will say that x is out of scope when you're inside the f function. Okay, so without getting into the debate of whether it's a good thing or a bad thing, let's just consider what is actually happening here. Okay, this y here is what we call a bound variable. Okay, and it's bound because its name appears in the function header. So whenever we use the name y, we mean this y up here. Okay. Whereas this thing is what we call a free variable, and it's free because from the point of view of the function, it doesn't have any obvious value. So in Python, there's an extra rule that says when this happens, go and find x wherever you can, go and find it somewhere else. And so Python is very kind of fluid with its scoping rules. Okay, so this is called scope, the scope of a variable. But Python is often criticized for being too lax about its scoping rules, and this does lead to bugs in a lot of places. But we're going to take that same concept and we're going to define it in the lambda calculus. So we're going to define a variable as being bound if it occurs inside a function's expression and also inside the function's name. So for example, okay, let's consider that identity function again. This is the function that takes x and returns x. So this x is bound, and it's bound because its name appears here as well, okay? And you can see that the meaning of this is that x is just going to be whatever is used as the input. It doesn't matter that we're using the symbol x. We could just as well have called this lambda y that returns y, and it would have exactly the same behavior because y is bound again. Okay, whereas in this function, x is bound because it appears over here. So both of these x's are bound, but there's also this y and this z sitting over here. Okay, and these are free. The x's are bound and the y and the z are free. Now the free variable is behaving very differently now because x is an input, but y and z are just floating around as symbols. So for example, if you applied that function, let's say we apply it to the number 3 as an input. Let's do an application. What are we going to get? So this is the function that takes x as an argument and it returns x, y, z, x, and we're giving it 3 as an argument.
Well, in the grammar that we define, we don't have 3, but with 3 as a symbol,
Yeah.
this is surrounding just the symbols y and x with the symbol 3.
So yeah, okay, this is a little bit informal actually, but yeah, assuming we're allowed to do that, then that's what it'll evaluate to. So you can see that the symbols y and z are behaving very differently here because you're actually getting those symbols in the output. You're getting those particular symbols. So you know, we could very easily rewrite this function. We could write it, for example, as lambda a, which returns a, y, z, a. Okay. And this function would behave in exactly the same way. But if you try to change the y and the z, let's say you turn it into a c, d, a, now you have a different function because now you get out 3, c, d, 3, which is a different output. So you can see the way that a free variable and a bound variable work is different. You can change the bound variables without altering the function. But if you mess with the free variables, then you get in trouble. Okay, so let's look at some more examples then. Which variables are bound and free in this expression?
Technically, I think it depends on what level of scope you're at, right?
Okay. What variables are bound in what scopes then, if you like?
Well,
would the first x be bound and the second x be free? Because technically the second x could be any name, and it would still come out with like a single variable or a single name.
So these are both bound, right? These are the same variable, really.
Yeah.
If this is saying that's the input and that's the, yeah, okay, if you call that the first x. So these are bound, yeah? And what about this one?
That one would be free, I think.
That's free, yeah. So a good way to see the difference is ask yourself, would it change the result if I change the symbol, okay? So if I rewrote that as lambda a that returns a applied to x, what's the result of that?
That would still be x.
That would be x. Yeah, good. But if I change the other x, if I change that one to a, what's the result of that?
That would be a.
That would be a, yeah? So this has not changed the result, this has changed the result, and that's because here we've changed a bound variable, and here we've changed a free variable. Okay, so you're allowed to rename bound variables, but you're not allowed to rename free variables. Okay, good. Okay, let's do another one. How about this one? Feel free to draw on the screen if you like. Which variables are free and which are bound in this one?
I think it's a bit. All of the x's are bound, but no of the other variables are bound.
Okay.
That was my thought.
Sounds good. Yeah. Sounds good. All right. How about the last one?
Let's see. You put the pen thing on. No, actually, it's not that difficult. The second half of the application, y is free and x is bound.
X is bound.
And in the first half of the application, all of the x's are bound, including inside that inner function.
That's including the one in the inner function. Yeah, that's right.
Yep.
And then anything else bound?
And the w is bound within that function.
That w is bound. Good, good. And the z's are all free. Okay, good. Okay, so this looks scary, but it isn't. This is only scary because I'm trying to be as formal as I can. And as with all these slides, they're brand new and it's perfectly possible there might be some little bugs in them. So please let me know if you find them. These are the logical rules of lambda calculus, so otherwise known as the semantics. So we've seen the grammar, that describes the syntax of the language. These rules describe what we do with lambda calculus. They describe that process of how a function gets applied. And lambda calculus only has two rules. So these are similar to the rules you've seen in the MU system, right? If you plug in stuff at the top, then you're allowed to write down the thing at the bottom as your next theorem. Now, there's really only one rule, and it's this part and this part, and everything else is there just to fiddle things to make them work. Okay, and roughly this is saying if you've got a function, look, here's lambda x that returns m. If you've got a function and it's being applied to something, so there's an application. In this application, you've got a function and an expression n. So roughly, if you've got that, then you are allowed to write this. Okay. So a and b can be anything. These are just other bits of the string that you're not going to touch. We're only going to manipulate this function application. So look, we've left a and b alone. And what we've done is we have written m, and this notation means with n substituted, so with n substituting for x. Okay, so this is the formal definition of what we've been doing all along, right? It just means if you've got lambda x that returns x plus 3, and you're applying it to n, where n could be anything, you are going to discard all of that. You're going to take this thing m and you're going to rewrite it substituting n inside of m. Okay. So again, this is a syllogism or a sequence. Now this is really the only main rule of lambda calculus. Okay, everything else is there just to tweak a few things. Does this not make sense to anyone? Okay, there's a bunch of exercises on this in the chapter 1 that I gave you from the lambda book. So look, that's the main rule of how you evaluate a lambda expression, and we call this beta reduction. Okay, when we write a little name next to a syllogism, we're just giving it a name, as we did with bang and pop in the MU system. Okay, so everything else here is just around to smooth things out a little bit. There are problems when you get the same variable names showing in as an input as an output. So I'll come back. This is a condition, okay? This is saying you're only allowed to run this syllogism if that condition is met. Okay, so it's here you're saying look at all the free variables in n and look at all the bound variables in m, and if they intersect, then you're not allowed to do beta reduction anymore. Okay, you're only allowed to do this if there aren't any free variables in n that also occur as bound variables in m, and it's there to avoid a type of name clashing. Let me give you some examples. Okay, these are examples that work nicely, and you can do them only with beta conversion. So would anyone like to draw on them and explain what is going on here? Someone have a go. This one's easy, right? We've already seen this. What's going on in this sequence?
No? Okay. Well, the first one's simple enough. We take we have a function, and we're applying it to y. So we replace all elements of y. I think the notation for this is like I don't remember which way around it is, but you like do.
I can never remember either.
Yeah.
Yeah.
In English you'd say you replace x with y. So
Yeah.
I like this way around.
Okay. So yeah, this function was, it's going to return this thing, but we're going to plug that y in to replace it. Yeah. Good. Okay. What about the next one?
Isn't the next one just the same thing? You're doing the same substitution,
Yeah.
but you're replacing both x's, so you get two y's.
Yeah. So we've applied the beta rule, okay, the beta reduction rule, and we've taken that expression and we've substituted y for x to get this. Yeah. Okay. Good. And how about the third one?
Is anyone else having terrible connectivity problems, or is it just me?
Yeah, I've been having some people like their voice and videos have been a bit noisy.
I've had pretty hard delays on writing on the screen.
Yeah, it keeps on disconnecting me. But then when it says you're reconnecting, it never reconnects me, which is really helpful. So it's currently saying that I'm reconnecting. I've got audio, but it doesn't show me the slides that are being shared.
All right, so look, in the third one then, we've got to do this in two steps. Okay, we're going to apply the beta rule once, and look, here's our input. We're going to plug that in, and it's going to become x. Okay, so now we take xx, and we rewrite that, but we're substituting the argument for x. And so that xx has now become the next line, okay, because each x has become a copy of the input argument. Okay, so you can see we've evaluated it once with the beta reduction rule, and we've got another lambda expression, and we can still go and do some work on this as well, because this is now another function application. It's this function applied to this function, and you can probably convince yourself that the result of that is z, because this is the function which takes y as an input and it returns free z. Like z isn't bound, so you just get the letter z coming out. Okay. So this is all very nice.
Quick question about that one. If it's like there's both yz and yz, so why would you not get two z's?
Okay, this is the function. Okay, read it in English, right? It's the function which takes y as input and returns z. Yeah.
Yep.
So this is the input. So this is going to become y. And remember, the rule of beta reduction is that we're going to take this. This is what we called m before. We're going to take this expression, and wherever we see y in it, we are going to substitute the input. We're going to substitute lambda y that returns z. The thing is, there aren't any y's in this expression. This is just a z. So we don't actually do any substituting, because z is free. So it's just pops straight out.
Okay, I get it now. It's sort of like there should be, it's like one sort of missing where it's yz and then getting rid of the y, but you've done that in the same beta reduction. I got you. Okay, that makes sense. Thank you.
Good. So this all looks very nice, and this is what Church wanted lambda calculus to behave like. There are a few cases where things get annoying because the variable names will clash, and so these other rules exist to just smooth out those problems a little bit. So let's consider something like this. Okay, what you have here is, okay, the overall structure of this is an application, right? This is a function. It's getting that argument y, okay? Now the problem is that inside this function, we've got another variable called y, and it's bound. Yeah. You see this y here, and this is going to clash. If you try and plug that y input in directly, you will get something bad happens. Now, do you remember I said if you've got a nice bound variable, you can just rename it without changing the meaning of anything? Yeah. Doing that is what we call alpha conversion. So to make this work, before I actually evaluate that function, I'm going to check, is there anything here that is going to clash with anything in here? Okay, and I see we've got a free y and I've got a bound y, and that's going to cause a problem. So before I do the beta reduction, I'm going to rename some variables to avoid the clash. Okay, and remember, I'm allowed to rename bound variables, so I can take that y and just rename it as z. Yeah. So remember that, for example, the lambda x that returns x is the same thing as lambda y that returns y. Yeah, they're the same function. They're both expressing that identity operator. So in general, are you happy with this? Are you happy that this pair of functions are the same? Anyone not happy with that? Yeah. Okay. So look here. Then I've applied the other rule. That is the rule of alpha conversion. And alpha conversion says I'm allowed to rename bound variables however I like because it doesn't change anything. So after I've done that, I've now got a much easier thing to clear up here because now I've got rid of that naming clash. Now I can just apply standard beta reduction. I'm going to take that y, that gets fed in as x, yeah, and that x appears here. So you can see the result is this expression. Now I've got lambda z that returns y z. Yeah. So notice this is interesting because the output has a z in it and there weren't any z's in the input. But it's okay because it's a bound z, so you can call it anything you want. You can call it John and it will still work. Well, it would if you were allowed to have my original A to Z rule. You could call it John in lowercase. So the process I just went through there is written formally back on this definition slide, okay? Remember, this is the real rule of lambda calculus is just beta reduction. That's really what we want to do. But I've put a condition on it here, and I've said you're not allowed to do it if anything that's free in M overlaps with anything that's bound in M. Okay, you're not allowed to do a beta reduction if that is the case. So if you do encounter that case, as we just did, remember I got to, yeah, I was on this line and I wasn't able to do a beta reduction because I'd violated this side condition. Yeah, so I think that's the main condition. We call this a side condition because it's just something that you have to fulfill to be allowed to use the rest of the rule. So when I hit a case like that, that means I'm going to have to do something else. And the thing I'm going to do is this alpha conversion. So this is the rule, the syllogism for alpha conversion. And this is simply saying, again, ignore the side condition on this for a moment. It's saying if I've got a function like this, lambda x with m, I'm allowed to rename that to anything. I can rename it to lambda y as long as I swap y for x. Yeah. Anyone want to explain the side condition on this?
It's saying if. Oh, sorry. Please.
Okay. Suppose I've got a expression like this. Am I allowed to rename x as y?
No. So what the e symbol is e for element. So it's saying if y isn't an element of the set M.
Mm-hmm. Yeah. Yeah. Okay. So it's saying I'm only allowed to do an alpha conversion if I pick a letter that isn't already in the expression. Yeah. So I can rename x to z. I could rewrite this thing as lambda z that returns zy. That would be okay. Yeah. So I can pick any variable name I like as long as it doesn't clash with one that I've already got. So in this case, there's already a y in the expression, so I'm not allowed to do this because that would change the meaning of the function. Yeah. So you can see this is now a function that takes an input and returns 2 copies of it, and that's a very different thing from just taking an input and adding the letter y after it. So here we call z a fresh variable. That means a variable that isn't currently in use in the expression. So another way of explaining this is, instead of saying y is not in M, you could say y is fresh. You'll sometimes see that in the books as the side condition. So this alpha conversion stuff is just fiddling around, really. All of this is really about this rule of beta reduction. And the alpha conversion and the side conditions are just to avoid those difficult situations. And it's always, alpha conversion is a weird concept. It's always explained slightly differently in every book. And I'm going to give you an implementation of lambda calculus. So I've got to say I don't completely trust the way that it implements alpha conversion. It may well be buggy because it's just something that I found on GitHub. So if you find any problems with alpha conversion, let me know, and maybe we could even fix them in these implementations. When you do lambda calculus with a pen, you will very quickly understand intuitively what alpha conversion is and how it's needed. It's quite famously hard to actually explain. So, this is my own notation. This isn't copied from a book. This is how I've explained it. I hope that this is right as well. If you find any bugs with this, let me know. But you'll recognize it when you do it. It's very obvious when you're working through the chains of sequence when the beta reduction is actually okay and when it isn't. And it's not okay if it changes the meaning of a function in any way. Shall we take a tea break for 10 minutes?
Yeah, sounds good.
Yeah.
Sounds great.
I have a question. So in terms of alpha conversion, I know there's a bunch of different, after the lambda calculus, a bunch of people came up with different versions of the lambda calculus. I know about the type lambda calculus, for example. Is there any, I was toying with this in my head the other day. Can you have a generic algorithm that means that you never have to do alpha conversion? So if we just name things in such a way that there's never any clashes within different scopes by so if I have a lambda and it binds something, then every instance of the thing that it binds, I think I could replace with something that's the name of it, and then something that specifies its distance from that lambda. Is there any like formal way of doing something like that? Is there
okay. So yeah, since Church's original work, there have been lots of variations of this developed to try and do this kind of thing. So historically, the first version you'll come across is called combinator logic. So if you
the SKI,
SKI,
yeah? It's so beautiful, dude.
So it's kind of hard to understand what it means, but it's another way of writing effectively lambda calculus, but it removes all of the bound variables, so they just disappear. So mentally, you have to do quite a lot of work to understand what's going on in it. But that was the historically first method of avoiding having to do alpha conversion. So since then, I think that there have been several versions. That there are conventions for, just picking these new fresh variables. Every time you do something, you can create a new fresh variable. I think there's something called IOTA rule or something. Yeah, there's been a few of these things developed. Maybe we could look at them later in the module if it's interesting.
Yeah.
You'll sometimes see them
play with combinators, but I think IOTA was like a reduced version of the SKI combinators. It's So you implement basically the entire lambda calculus with like 1.5 combinators, basically, which is so silly. It's nuts.
Yeah, sometimes complexity has two different meanings, right? A proof can look very complex if it's long and it's made out of very small, simple things to one person. But if you're doing the meta logic for a system, then that proof is very simple because it's only using a very reduced chunk of logic that you then have to reason about. So yeah, there's a few of these conventions. You'll see them if you run some of these implementations and you notice the variables getting renamed to weird things, especially things with numbers on. That probably suggests they're using one of those later conventions.
Okay. Thank you.
Yeah. Good question. Okay, let's come back at 15:45 then for part 2. Okay.
You remember there's something on your face.
Is there?
It's a nose. No one knows that you have a nose. No? No. Nose?
Uh,
Nose, Jose.
what are you talking about?
Oh dear, how you doing, my man?
I'm good, thank you. How are you doing?
I'm doing pretty hell yeah. I'm doing absolutely magnificent.
Good. I'm glad.
There are
Ugh.
demons in your green screen. It's doing the thing where
Occasionally.
like a little riff on it, and it does a
Yeah,
little black shift.
fair,
Terrifying.
because yeah, it is slightly terrifying. Unfortunately, I don't have proper lighting. I currently am using this for like the back of my green screen. So
Well, you see, my
I'm getting a
backlight
better.
is literally just my light. You're doing better
Makes
than
sense.
me, man. It's
I'm trying
a
to fix
sick
the
ass
light.
background though. Where is that from?
It
That's
is.
amazing.
This is from a computer museum in Seattle. This is digital DPD-8E, and it's mirrored. That's the terminal, as you can probably tell. But yes,
That's gorgeous.
microcomputers. It is nice. I can't see it. I don't know why I'm looking backwards, but yeah.
Oh, fantastic. Nah,
Yes.
it's good stuff. It's got exactly the aesthetic that I'm looking for, really.
I like it. And it matches my lighting alright as well. Just, once I get better lighting for the back of here, it'll get rid of the demons, so it'll look better. But for now, the demons are just kind of residing.
Oh, yeah, no, some of the battle stations back at home. Oh, it's legendary. I've got one of these standing desks, which is a desk but higher up and heavy, because
Smart.
otherwise it falls over.
Yeah. I wish I had a standing desk. My leg keeps my right leg keeps just being painful because I'm sat down for too long and then it just hurts. It's just annoying. I wish I had a standing desk, but alas,
Yeah.
I'm stuck with this low boy.
Yeah, it's I don't know. I think I prefer standing up, but that's just because
Yeah.
I wander around a lot. And again, like you said, I was starting to get to the point where I'm spending so much time sitting down hacking that unless I set like an alarm to have regular breaks, my legs start cramping up, basically.
Yeah.
God,
Like an
getting
Alexa
old,
import.
Rimmer.
Oh god, everyone's taken. Back's curling up. It's too late for us.
It comes on faster than you know, guys.
Hello.
Oh dear.
Oh my days.
I always lean to my left ever so slightly, lean on my arm to my left, and it sort of tightens up on my sort of left-hand side. So then when I stretch, it's tricky. How do you wind it? Is it a wind-up desk to raise it, Matthew, or is it a push-button electronic one?
This one.
No, the Matthew Murr. You got a standing desk, you said.
Yeah, no. I don't know if I would ever buy one. I got this one for free.
Oh,
It's honestly just a tall desk with some pneumatic things, so you can change the height of it.
yeah.
And you don't need to change the height of it after you've got it to the height that you want it to be. So just go into your garage, get a plank of wood, and then find a good height for other planks of wood that you want to affix it to your next desk on, and you're set. Yeah. But no, it's nice being able to stand up. I don't know about actually having a standing desk in the commercial sense. So.
All right. Welcome back, everyone.
Oh,
Sorry, I didn't mean iotas. I meant this thing. I posted in the text chat. It's called a De Bruijn index. Yes, iota is a combinator thing. This is a pure alpha avoidance thing, if anyone's interested. Good question, though. Yeah, alpha conversion is a pain. It's very good stuff to know about. It comes up in real life in a whole bunch of things. So I thought I'd just give you an example of a paper I was writing last week, which has a bit of this in. I think some of you guys know I'm a musician, right? So I do some research on computer music applications. Let me just share my screen for a sec. So this is a compiler I'm doing for a music description language. It's going to take hierarchical structures and compile it into MIDI ultimately. So the idea is you're going to write things like this. You can say, you know, a verse of a song is an X and a Y and an A and a Y and a Z and so on. And then you can define, there are standard musical structures like a turnaround. There's a 4-chord and a 5-chord. Well, there's a whole bunch of these things. You know, a bounce is when you go down to the 7th chord and back to the first. Or you can define a standard structure like this. Yeah, this is a verse, chorus, middle 8, verse form. And so the idea is you can notate an entire song very concisely using this notation. So, for example, this is a Beatles song. This is Hard Day's Night, and you can define the entire song just like this in terms of this grammatical hierarchy of structures. So it turns out to make this work, you run into that alpha conversion problem all over the place, because you can end up with two different things that have both temporarily got called a verse or A or a B. And so, you know, this isn't lambda calculus, this is a different language, but the concept that I've learned from lambda calculus has been very useful, because when this problem showed up in the music language, it looks like alpha conversion, and you can then say, aha, we need some alpha conversion, and then you know what the remedy is for that particular type of problem. So the reason we study systems like the lambda calculus is as models of computation, and we see these concepts, and then those concepts are going to show up in real life. And when you've seen the model version, you now know what it is. You can give it a name, and you know how to go out and deal with it. So
even if you're not the person writing the language, C++ name mangling, that's still a big controversial thing within there. But it is the same thing. That's interesting. That's a good way of thinking about it. Writing that down. That's wisdom.
And you know, there's one particular compiler writing project I'm involved with right now, which I'm pretty certain is about to run into a whole bunch of scoping related problems. And if the people involved in that had studied lambda calculus first and understood what being free and bound actually means, then their life would be a whole lot easier if they had those concepts before they start diving into writing the assembler code for it all. Not to mention any names. Okay, so look, I'm going to put you guys into groups in a minute to just talk through some of this and try a few things out. I just wanted to introduce a couple of concepts first around what is called syntactic sugar. So when you do anything with lambdas at scale, you will very quickly run into what is called lots of insidious, silly parentheses problem. That just means getting brackets all over the place. I've so far given you this very formal syntax, and if you remember, this requires putting a bracket around every function application and every function definition. Right? If I go back to the grammar slide, you can see we introduced brackets here and here. And when you start to write anything remotely large, you will soon just get this big mess of brackets and lambdas all over the place. So there's a couple of informal conventions that everybody uses just to make the notation easier for humans. And if you write a lambda calculus interpreter, which I hope some of you will do, you will often need to implement this as a front end. The user is going to want to write in this simplified, we call it syntactic sugar, right? It's like sprinkling sugar on the notation to make it more palatable. So there are very simple rules for converting between the formal notation and the sugared version, and I'm just going to go through them here. So there are two rules. One is called the lambda scope convention, and one is called the evaluation convention. So the lambda scope convention means we're going to allow you to omit some of the brackets, okay? If you omit brackets on function definitions, we are going to assume that they bind as far right as possible. So easy to understand with an example. If we write, ignore the bit on the left first of all, just consider this thing, okay? This expression is not well defined according to the formal grammar I just gave you. This expression is. This is directly from the formal grammar, or almost. But we're going to assume that the position of these brackets is implicit and it always goes in this way. So if someone gives you this, it means this, okay? And if you're writing an interpreter, the first thing we're going to do is clean this up by actually putting the brackets back in again. And there's a one-to-one correspondence, so that there's no extra information in either representation. So here we're just saying you can have a whole bunch of lambda functions and collectively they're going to return x, y, z. Okay. So we'll also reduce the amount of notation then by writing it like this. If you see lambda x, y, z, that's just shorthand for this lambda x dot lambda y dot lambda z, which in turn is shorthand for that. Okay. So I'm sure you agree it's a lot easier, especially when you do pen and paper exercises, it's a lot easier just to write this than it is to write this all the time. So a nice exercise which you could try in your groups if you like is to write a program that does this. You convert from the shorthand into the longhand versions and back again. So the second convention, this one is to do with function definitions, right? The second one is to do with the applications, and it's a similar idea. We're going to assume that brackets can be omitted, and so if someone gives you this, if they give you A, B, C, D, E, what they mean is this, okay? And this is a whole bunch of expressions, and they're going to get evaluated in this order. So it means first you evaluate A applied to B, then all that applied to C, then to D, then to E, okay? If you want them to be applied the other way, something like that, then you're going to have to write the brackets in longhand. But this is just a syntactic convention that says if someone gives you that, let's assume that it means this. Okay. So nice exercise. Try and write a program that converts both of these conventions between the long form and the short form. And very useful when you're doing pen and paper exercises. It helps you to not go crazy with the bracket. So then finally, I think for today, I wanted to introduce you to PyLambda. So this, I don't know if this is the best or even a good one. It's the best one I've found so far. This is an implementation of lambda calculus as a programming language. I'm going to give you a link, not this link, because it only worked on Python 2. I'll give you a link to my GitHub where I've done the Python 3 port. So in your groups, I'd like you to get this installed. I've given you instructions for running it. It's written in Python, hence PyLambda. For those of you who know Flex and Bison, it is basically sitting on a Python wrapper of the Flex and Bison compiler tools, also known as Flex and Yak. So it's sitting on a library called Ply. This stands for Python, Lex, and Yak, which are these compiler writing tools put into Python. So if you can get this up and running, you'll need to install Ply first of all. I've given you an instruction for that. I've given you a copy of the Ply library as well. When you run it, you can run it with make run. Slightly strangely, you'll get into a Lambda calculus interpreter, and this is interactive. Like so, it's common to write the symbol lambda using this slash. That's the slash on the left-hand side of your. Is that the left or the right-hand side? Which slash is that? It's the left-hand side of the keyboard. Sorry, next to the Z key, and that's supposed to symbolize lambda, right? It's common in software to use that slash because we don't have a key for lambdas. Some of these things will actually replace those slashes with a Unicode lambda. So actually, ML has been doing that for about 30 years, very successfully. In other cases, you'll just see the slash used. So this is interactive. Here's the prompt, this little arrow. So that here I've typed, this is the function which takes x as an input and returns x applied to y. Yeah, and that's going to get evaluated, and the result comes back. It's y. Yeah, y was the input. It's got copied twice. Here's a couple of other evaluations, and yeah, you can build up pretty complex lambda expressions out of this. So I'd like you to get in your groups and get this set up on your own machines and just have a play around with it, really. Please have a look at some of the expressions from the slides from today, or if you've been doing any of the readings, you can find lots of lambda expressions in those readings in the books. Just have a play around and try putting in some lambda expressions, and maybe try doing some with a pen and paper as well, and convince yourself that the answers you'll get back from PyLambda work and give you the same answer. So like I say, I'm not entirely convinced by some of the alpha conversion stuff that it's doing. If you find those, let me know, because it's interesting. I had some more slides, but I'm going to save them till next week, I think, on church numerals. Let's put everyone into those groups in a moment then. So you'll see some of the syntactic sugar conventions sitting in PyLambda. Here's how you git clone it. You will need to set up that Ply library before you run it. Have a look at its README file, because it takes you through a bunch of things that it can do. If you don't like it, there's another one I found more recently here you could try out. So let's all jump into some groups. We'll try evaluating some lambda expressions from the slides that we've seen today. Let me know any errors. And then I'd like you to think about a couple of questions here. What happens if you evaluate this expression? Can you find other expressions that do something similar? If you get through all that, why not have a look at the exercises from the book that I gave out, talk through them in a group, maybe use PyLambda to evaluate some of them and check them. Probably not here in the workshop, but if you want to take things home, please have a look at the PyLambda source code, talk through how it works, try writing a desugaring program. Part of the assessment for this module is basically describe how a lambda interpreter works. So this is directly accessible stuff. This is what we really want you to take away from the module. But I suggest working through some of this stuff in your groups first, and maybe taking this away with you later in the week. To form the groups, could I suggest we've had 4 people have presenter rights at the minute. That's Elliot, Gary, Matthew, and Matthew. Could I suggest you 4 create or sit in the groups numbered 1, 2, 3, and 4, just so we've got the 4 most talkative people each in a separate group, and then everyone else join any of the 4 groups. Try and, how many people per group are we going to get? Probably about 3 or 4 at this rate. So let's make Elliot in group 1, Gary in group 2, Matthew group 3, or the Matthew group 4, and then everyone else jump into those they're already set up on the blackboard. And then I'll come around and have a chat with you all about it. Does that make sense?
Yeah, super.
Sounds good.
Okay. So let's break out, and I'll see you in the rooms. Okay, good. And I guess we can all come back in this one at whatever 4:55 just to rejoin. Okay. So see you there.